The question that I have is, could you define stress? Let's start with the simple definition of stress. Stress equals force per unit area. Just to give you an example that you could relate to, consider this table that weighs 100 pounds. This table is supported on 4 legs and therefore each leg carries 25 pounds. If you place this table on a carpet without leg pads, you know what will happen under the legs, right? After a while, you're going to see a little indentation on the carpet under each of the 4 legs, right? The indentation can be greatly reduced by using leg pads like this. Well, how did the leg pads eliminate the indentation? Each leg is still carrying the same force, 25 pounds, right? So the difference is in the stress, not the force. At the contact between the legs and the carpet, the stress, which is the force per unit area, is very high here, very low here. So this is what prevents indentation from forming under the legs when you use leg pads. Let's consider one more example from statics. You guys remember this kind of problems, right? From statics. Particle or particles supported on cables. Let's analyze this cable AB a little bit more. We know the cable is subjected to a tension of 50 pounds, right? Let's take the cable AB, section it at a point like point C, separate into 2 parts and consider the equilibrium of the top part. What kind of internal force am I going to see at point C? I'm going to see a tension of 50 pounds, right? Supposing, say, this cable has a uniform cross-sectional area of 2 square inches. Now remember, in the definition of the stress, the average stress at point C would be force per unit area, right? So that will be 50 pounds divided by 2 inch squared. That will be 25 pounds per inch squared, right? And this is what we call 25 psi or pounds per square inch. And you can see for the same tension of 50 pounds, if the cable had a bigger cross-sectional area, the stress would have been smaller. Or on the other hand, if the table had a smaller cross-sectional area, the stress would have been higher, right? Notice that I used the phrase average stress to describe this, right? We will talk more about this later, but here is a quick explanation. Depending on how far away point C is from point A, the stress at various points on that cross-section may not be the same. If the cable AB is held on this ring at a certain point, then this tension of 50 pounds is not going to be spread uniformly on that cross-section. What that means is if C then is very close to point A, this stress is not going to be uniform at all. But it turns out as you move farther and farther away from point A, then the stress becomes uniform. So what we can meaningfully define is an average stress. So that's why I used the phrase average stress. With this cursory introduction of stress, here are 2 questions that come to mind. What kind of stress is sigma average? Why do we even bother defining a stress? Why not use force? We'll answer the first question in this video and the second one in another video, right? Now let's consider a 3-dimensional body like this. The body is subjected to external forces like these and supported like these. Let's say we want to section the body along a plane like this and then try to understand the stress on that plane. Now remember, in the earlier slide we talked about the fact that even on a 1-dimensional cable, the stress may not be uniform in the cross-section, right? Now this is particularly true for a 3-dimensional body like this. On this plane, the stress is going to vary from point to point. In other words, stress at point 1 is not going to be the stress at point 2, which is not going to be the stress at point 3, which is not going to be the stress at point 4, and so on. In general, of course. A further question that comes to mind is, what is the direction of the stress? Well, in the earlier cable problem, we could say, well, the force, the tension on the cable, is in the direction of the axis of the cable, right? And therefore the stress is presumably in the same direction, right? But on this plane, we don't even know the direction of the force, and therefore, what is the direction of the stress? with the two issues we raised in the earlier slide in mind, which are the stress on a cross-section may not be uniform and we don't know the direction of the stress, right? Well, let's go ahead and define the stress as follows. Since the stress may be changing from point to point, we resort to calculus here. We're going to consider a little differential area dA at any point A. Let's say the force vector on the little differential area is dF. Now remember, force is a vector, right? It could have three components in general. So let's go ahead and define a three-dimensional XYZ Cartesian coordinate system right at that point. Let's take the axes X and Y to lie on that plane and Z to be perpendicular to the plane. Now let's express this force vector with respect to this coordinate system. In other words, its component in the x direction is dfx, component in the y direction is dfy, component in the z direction is dfz, and therefore vector df equals dfx times I plus dfx times j plus dfz times k, where I, j, and k are the unit vectors along these three axes, x, y, and z, right? In the cable system, we just had one force, right, which was the tension in the cable, and therefore we define one stress. But here we have three different forces, dfx, dfy, and dfz, and therefore we could define three different stresses. And that's what I have done over here. Note that we are still using the same old definition of the stress. Stress equals force per unit area. So I took the force components and divided them by the same area, dA. Let's make one significant observation about the direction of these forces. Two of these forces, which are dfx and dfy, are forces lying on the plane, right? Whereas dfz is a force perpendicular to the plane. The stress that go with the force that is perpendicular to the plane is called the normal stress. The stresses that go with the forces that are on the plane are called the shear stresses. We're going to talk about the notations more a little later, but for now, this plane can be called the z-plane, the plane that is perpendicular to the z-axis, right? So one of those subscripts here indicate that. The other subscript indicates the direction of the stress itself. So this is a stress in the z direction, this is a stress in the x direction, this is the stress in the y direction. So within this framework, if you were to go back and look at the cable system one more time, what kind of stress is sigma average? Well, sigma average is a normal stress because we know the force is perpendicular to this plane, and therefore the stress sigma average is also perpendicular to this plane right there, and therefore it is a normal stress. In the analysis we discussed in the earlier slide, we took the 3D body and sectioned it along a plane like this, right? Then we focused on the point A. Supposing, say, instead of sectioning it along this plane, I section it along this plane, a plane that still passes through point A but has a different orientation now. You think that force on that little differential element is still going to be the same? The answer is no. In other words, dF1 is not going to be the same as dF2, which means the normal stress and the two shear stresses depend on the orientation of the plane. So what do? Well, it seems to keep getting more and more complex, right? Well, this is what we do. We define one global Cartesian XYZ coordinate system like shown in this picture. Define a differential cube with respect to this coordinate system. In other words, we define this cube such that their faces are perpendicular to the three coordinate axes, x, y, and z. In each of these planes or faces, there will be one normal stress and two shear stresses, right? Since a 3D cube like this has 6 different faces, we come up with 18 different stresses, right? But it turns out that the equilibrium equations allow us to reduce the number of stresses from 18 to 6. Let me show you that in the next slide. Just to keep things simple here, we'll consider a two-dimensional state of stress like shown in this picture. In particular, I'm considering the YZ plane here. There are 4 different faces to this two-dimensional differential element, and each of the faces has a normal stress and a shear stress. Supposing, say, we let the size of this differential element approach to 0. In other words, we let dy and dz approach 0. Then this differential element basically shrinks to a point, right? So this plane and this plane become one and the same. And similarly, this plane and this plane become one and the same. Based on Newton's action-reaction principle, we know that if we section a body somewhere, the forces on either side of the section must be equal and opposite, right? So when this plane and this plane coincide with each other, they become like a section, all right? So what that means is sigma z and sigma z prime must be equal to each other. Sigma y and sigma y prime must be equal to each other. Tau zy and tau zy prime must be equal to each other, and tau yz and tau yz prime must be equal to each other. At this point, we haven't proven that tau zy and tau yz are equal to each other, which we will do right now. To do that, what we do is we take a moment about point A for the forces acting on this differential element. Since we already showed that sigma z and sigma z prime are equal to each other, the forces due to them are equal to each other, and therefore moment about point A of these forces will cancel out, right? The same is true for the forces due to these stresses. And of course, these shear stresses are passing through point A, and therefore they have no moment contributions. So the only two forces that are going to show up in this moment equation are forces due to this shear stress and this shear stress, right? So that's what I have over here. Remember, you need to multiply the stress by the cross-sectional area to find the corresponding force, right? These are 2D elements, so we consider a unit length into the paper. So the cross-sectional area of this face, for example, would be simply dy multiplied by 1. And therefore, the moment of the force corresponding to the stress would be tau zy multiplied by dy times dz, which is the moment arm of that force. All right, now you get the idea, right? So this leads to this conclusion. That is, tau zy equals tau yz. And these are called the complementary shear stresses. So on the basis of the above, the number of stress components is reduced from 18 to 6. 3 normal stress components, sigma x, sigma y, and sigma z, and 3 shear stress components, tau xy, tau xz, and tau yz. It can be shown that the stresses on any other plane, such as plane AB in this two-dimensional situation, can be found in terms of these 6 stress components we just talked about. These 6 stress components. So when we started this discussion, we were not sure how we were going to define the stress at a certain point, right? The state of stress at any point in a body can be uniquely defined in terms of the 6 stress components, sigma x, sigma y, sigma z, tau xy, tau xz, and tau yz. Remember, to define a force in 3-dimensional, we need 3 components, right? But here we need 6 components to define a stress. So obviously it's a little bit more complicated than the force. However, not all 6 components are non-zero in all cases. So this is how a 3-dimensional problem simplifies to 2-dimensional problems, and 2-dimensional problem simplifies to 1-dimensional problems. For completeness, let's go over a couple more things here, starting with notations. One common way to present the state of stress at a certain point is to use the matrix notation. Remember, we proved that the complementary shear stresses are equal to each other. We had 9 stress components, right? And you put those 9 stress components in a matrix like this. The first row here represents the stresses on the x-plane. That will be this plane right there, plane perpendicular to the x-axis. The second row represents the stresses on the y-plane, and the third row represents the stresses on the z-plane. The first column here represents stresses in the x direction. So for example, if I come back to this cube here, sigma x is a stress acting in the direction of the x-axis, right? And similarly on this plane, we see this tau yx is acting in the x direction. Tau zx on this plane is acting in the x direction, right? And you see those are the three components we have on this column. This column represents the stresses in the y direction, this represents the stresses in the z direction. And therefore, the way you read this is sigma xx is the stress on the x-plane in the x direction. Tau xy is the stress on the x-plane but in the y direction. Tau xz is the stress on the x-plane but in the z direction, and so on. But because we have proved that the complementary shear stresses are equal to each other, there are only 6 independent stress components in here. For example, tau xy is equal to tau yx, and similarly tau zx is equal to tau xz. In other words, the components above this diagonal are equal to the components below this diagonal. Let me also introduce this terminology that you probably haven't heard of so far. Stress is called a tensor, T-E-N-S-O-R. Remember, mass is a scalar, right? We only need one component to represent a mass. Force is a vector. We need 3 components to represent a force. Stress is a tensor. You need 9 components to represent a stress. But of course, with the complementary shear stresses, it reduces to 6 components eventually. It turns out there's a simple formula that tells you the number of components that you need for these quantities. 3 to the 0 for scalars, and 3 to the 1 for vectors, and 3 to the 2, 3 squared for tensors. So you get 1 out of this, 3 out of this, and 9 out of this, right? So here's a little note about the complementary shear stresses and how the 9 stress components reduces to 6. So now let me ask you the question. In general, how many stresses are at a certain point? The answer, there's only one stress, but 6 components. Even though this is the correct way of looking at this, in practice we tend to be sloppy sometimes, right? It's pretty common to say stresses on a plane, although strictly speaking, these are components of the stress at that point on that plane. Another question, is the stress at a point is always 3D? The answer, no, there are situations where A, the stress is truly 1D or 2D, B, the stress can be approximated into 1D or 2D. So even though the stress analysis seems pretty formidable at this point, most problems that we run into have pretty simple state of stress, and therefore the corresponding analysis is not too bad.